the record, your permanent record of the experiment. The report sheets aren't your permanent record. The report sheets are, you give them away, you might not get them back. If your report sheets are your permanent record of the experiment, then you give it away and you don't get it back, then you have no record of doing the experiment. And so we do everything in the notebook. Notebooks, you don't have to keep those neat. Notebooks, you just want all your data there. The report sheets you do have to keep neat, and so just beware of that. So somebody remind me, what does conductivity depend on? Electrical conductivity.
Three things.
Three things, yeah. What three things? Mobility. Charge.
And number of those.
And number. Good. Yeah, that's good to refresh your memory on that. So for example, a test question could be, what three things does electrical conductivity? Even though I don't put that many lab questions on the test, there could be lab questions as well. And so we want to be prepared for those. So you review it a few times before the test, and then you'll remember it, usually. All right, what did we leave off on last time for the conductivity lab? So let's take a look. All right, I think saturated barium sulfate. Sulfates are all soluble except for which ones? This is another thing, unfortunately, you have to work at memorizing are the solubility rules. And so how do you memorize the solubility? You just repeat it. Like I said before, you repeat it or read it like twice a day or something. Through repetition, eventually it might sink in. What's that? How's your progress on memorizing the solubility rules? You're going to have them memorized, fortunately. You guys, can we start? Nicole, can we start? Thanks. The solubility rules, are you guys making progress on the solubility rules? Yeah? Try to get those memorized by the exam. The exam's next week. We're going to move the exam from Tuesday to Wednesday like last time. So we'll have the exam on Wednesday. For the chemical reactions, I'm thinking of trying to make it a little bit easier in that for the first exam, we'll probably just test you on one or two types of chemical reactions, not all of them. Otherwise, not the redox reactions. And so we're gonna cover some redox reactions here and some other reactions, but I think I'll hold off on those until later. On the last test, I waited until the end of the semester to test everyone on the chemical reactions, which turned out to not work very well. So this one will break it up into parts. So, but anyway, the question I had asked earlier was sulfate. Sulfates are all soluble except for which ones? Yeah.
It's all insoluble except for group 1 ammonia and
Oh, no, the other one, not sulfide, sulfates. Sulfate with a 8 ATE.
sulfate.
Yeah, sulfate. What's the formula for sulfate?
SO4
SO4 2 minus. So tell me the solubility rules for sulfates.
iron. Sorry. Yeah, iron, lead, mercury 2.
Not iron. Silver. Silver, yes. These are soluble except
Both mercuries.
silver, lead,
Both mercuries.
both mercuries.
Calcium, strontium, and barium.
What does it mean to be soluble and what does it mean to be insoluble?
Breaks up, the ions break up in the
The ions breaking up is not solubility, that's electrolyte. Yeah, electrolyte is like a non-electrolyte doesn't break apart.
when it dissolves.
Yeah, but there are non-electrolytes that dissolve, like sugar. There are lots of things that dissolve but don't break apart. So we have to treat these two things separately.
If it's soluble, it means that like greater than 0.1 mole would dissolve
Yes,
into water.
that's what I was looking for.
And if it's insoluble, it means that less than 0.1 mole dissolves into water.
Right, and is that an arbitrary cutoff or is that defined scientifically?
I believe it's defined.
Well, it's kind of an arbitrary. Somebody just picked 0.1 moles as the cutoff. You know, there's nothing specific. There's no like, okay, this has a solubility of exactly 0.1 moles per liter. So it's an arbitrary. So what that means is that different tables might have a slightly different set of rules depending on what cutoff they use for soluble versus insoluble. And so you're going to see that variation. So what we're looking at now is barium sulfate. Is barium sulfate soluble or insoluble?
Insoluble.
Insoluble means that the lattice is quite strong, and the lattice would be quite strong. Why would you think barium sulfate's lattice would be quite strong?
Because it's solid.
Yeah, so that's experimental evidence that the lattice is quite strong because it's insoluble, but is there any other evidence? Is there something else that kind of tells you that you would expect this to be a strong lattice?
Metal.
And so somebody remind me what Coulomb's law is dependent on.
Force distance.
Force is the Coulomb's law kind of measures the force, and so Coulomb's law says that the force is proportional to inversely proportional to the distance squared
And charge, right?
and the charge, right? And so it's going to be the charge over size. The smaller the size, the shorter the distance. And so it's if you want Coulomb's law, it's proportional to the charge over the size. We expect barium sulfate to be insoluble because of its high,
Size.
not the size, the big high charge, high charge. We haven't talked much about the size, but it's going to have high charge compared to some other salts because barium is what charge?
2 plus.
And sulfate?
Minus 2.
Yeah. And so 2 plus, 2 minus is going to have a stronger force than some of the other ones.
Electrolyte.
Electrolyte's different than solubility. So does somebody know the explanation why electrolytes and solubility are two separate things? Something could be highly soluble but doesn't split apart, like sugar. Sugar is quite soluble in water, but it doesn't split apart. So we have to ask these independently of one another. And so what we look at is something like barium sulfate's insoluble because this lattice is very hard to break apart. But what does dissolve? Does it break up into ions or does it stay together? as molecules, or what happens? Well, when an ionic lattice like this dissolves, the ions break up. And in this case, get surrounded by waters. So what we expect here is it's low solubility. In fact, it's low solubility because it should be insoluble, but being insoluble doesn't mean nothing dissolves. It just means below, what was that cutoff again?
0.1 mole.
Yeah, 0.1 mole will dissolve in a liter. And so, so we're going to get less than 0.1. I don't know exactly what it is. We could look it up in a book. But it's going to be less than 0.1, and what does dissolve should break up into ions because of the lattice structure. And so we end up with hydrated ions. And so for the conductivity for barium sulfate, what do you expect?
Or none.
Weak or no.
Yeah. Weak or none. Depends on how insoluble it is. And we have a just see. Let's take a look. Well, do you see something? Do you see a slight glow? Let me turn off the lights and see. It takes some time. Do you see a slight glow in the filament?
Very tiny.
Yeah, very tiny. Well, that's what we expect. It's insoluble, but a tiny bit does dissolve, creating a small current.
The barium would be a strong electrolyte.
Yes. It's an insoluble but strong electrolyte.
Soluble salts and strong acids and strong bases.
Yeah. However, remember there are different definitions of strong electrolytes. One definition is it's going to be a good conductor of electricity. Another definition of a strong electrolyte is it dissociates 100%. So a tiny bit dissolves, but what tiny bit does dissolve dissociates 100%. So even though it's a really poor conductor of electricity, we're still going to call it a strong electrolyte. It's a strong electrolyte with very low solubility. Now, when we do ionic equations, we want the major species. What's the major species here? Are the major species the ions, or is the major species the crystals? You know, this white solid at the bottom are crystals, tiny crystals of barium sulfate. Is the major species the solid or the ions in solution?
The solids.
The solid is the major species. So therefore, yesterday when I told you, what do you dissociate? You only dissociate the strong acids, the strong bases, and the soluble salts. You only dissociate the soluble salts because this is the major species. BaSO4 solid is the major species. And this is the minor species. When we do a chemical equation, do you want to list both the major species and the minor species?
Unless it's
It's going to complicate things. So what we do in chemical equations is we just list the major species. So if I had barium sulfate, I would classify barium sulfate as an insoluble salt and therefore leave it alone. Do not dissociate it. But when we're looking at the minor species and when we're looking at this in more detail, then we see, well, a little bit will dissolve because we could be, you know, at the higher end of 0.1 moles, you know, enough to cause a current to flow. Or we could be at the lower end, closer to zero. If we're closer to zero, we wouldn't have seen anything.
the minor species would be like barium.
Barium 2 plus aqueous and sulfate 2 minus aqueous. The bariums are the small dots here. The sulfates are the large circles here. So barium sulfate saturated is not a very good conductor of electricity because what?
Insoluble.
Yeah, I mean, as far as the three components, in science we usually try to talk about equations and the impact on the variables on the particular equation. So we're looking at sigma. Sigma is small because of which variable? And so we need to talk more mathematically sometimes.
Is the number?
Because of n, right, the number. The number is small because of its low solubility. And so that's what we expect. All right, let's move on to KClO3 solid. KClO3 solid, what do you expect to see for that?
Should we be soluble?
Hmm?
Can it be soluble?
No, solid. Just we're going to measure the solid, and so it's not the aqueous. So the first thing, we're going to just test the electrical conductivity of the solid salt. What do you expect for the electrical conductivity for the solid salt? Sigma 0, sigma low, sigma high. This is KClO3. What's the name of KClO3? Potassium chloride is KCl. Potassium chlorate is KClO3. That's correct. And so, is potassium chlorate solid, which is this white solid here? And so I'm going to get some scoops of this using the spatula here, or the scoop. They call these scoops. And I'm going to put it in this crucible, although you can't really see it very well. I'll show it to you here. So I have some salt crystals in this crucible here. What do you expect for sigma, the conductivity? Any weak?
And do how about a
Dim
dim light?
light? All right, let's check it. So we have 1 week. Anybody else? Venture a guess? This ring is... All right, I'll just hold it. Let me flip off the light. So you expect a dim glow for potassium chlorate solid? Do you see anything? Actually, there's nothing. I see nothing. It's not glowing at all. All right, so it turned out that there was no electrical conductivity. Why is that? Well, you should know something about solids. What type of motion do solids lack? They don't have translational motion. What do we need for electrical conductivity? We need mobility. Do we have any mobility in solids? No. So some solids we do, because they have channels. I showed you. I don't know if anybody remember, but the superionic conductor, remember the crystal with all the channels in it? And the ions could flow through the channel? I don't know if you remember that or not. But there are some solids that do have translational mobility, but not for everything. These so-called superionic conductors are class showing high ionic conductivity. Their structure, let's take a look at some images of these. The structures usually have these channels, like tunnels, that the ions can move in. And so this is like a subway tunnel through the crystal. And the ions have good mobility through those tunnels. And those will have some translational mobility, but not of everything. The tunnel structure is fixed. It's just these ions. Like in biology, we have ion channels through membranes. You know, it's that type of thing. This is important for transport. If we don't have ionic conduction, then we couldn't survive biologically. I mean, this is how electrical signals are transmitted. There's no copper wire in your body. And so how do electrical signals manage to get through? And so this ionic conductivity is very important for biologists. But it's also important for battery chemists, because battery chemists don't want to always work with water, because water sets a maximum temperature of what? About 100 degrees C. If you have a battery that needs to operate at higher temperatures, over 100 degrees C, then it's not going to work. Like, for example, the Tesla. You know, the Tesla, if you get like a Tesla, when you go to charge it, they do a preheating of the battery. And so if you don't preheat it, then they throw all these warning messages. You know, you didn't preheat the battery, and it it reprimands you for not preheating the battery, because then it's going to take longer to charge, and it shortens the life of the battery. You know, which I've done before, is not preheat the battery. And so the more you preheat the battery, the better. But you know, the batteries don't all operate at room temperature. There's some batteries that need to operate at higher temperatures. And if you have a battery that operates at higher temperatures, there's no way you're going to use liquid water as electrolyte, because it's going to limit the temperature to about 100 degrees C. Some batteries need to operate at a much higher temperature than 100 degrees C. I don't know what the optimum temperature for the Tesla battery is. It's probably online somewhere. I never looked it up. But that's if you get the Tesla. So you need to spend some time preheating it before you go to charge it.
So with potassium chlorate, would that be a strong electrolyte?
It depends on how you define it and what you're talking about. Potassium chlorate is a strong electrolyte, because if we were to dissolve it in water, it would be a great conductor of electricity. However, in the solid state, does it conduct electricity very well? No, it conducts as a very poor conductor of electricity in the solid state. Why is that? There's no translational mobility. Even though we have lots of charge, the potassium ions are plus and the chlorate ions are minus. No mobility.
So it's still strong, right? Electrolyte-wise?
It's still a strong electrolyte, because of the way we define the strong electrolyte is when it does dissolve, it breaks up.
Yeah.
And so, but, you know, the electrolyte definition, it depends on who you talk to. If you talk to somebody who's working with batteries, well, potassium chlorate's not going to make a great superionic conductor, is it? It's not going to make a great superionic conductor, because there are no channels in the crystal system, and it can't transport ions.
One definition for a strong electrolyte was that it has associated rotation. What was the second one?
Yeah, like you said, the first definition is 100% dissociation, or close to it. It doesn't have to be exact, you know. The second definition is it is an excellent conductor of electricity. Strong electrolytes should conduct electricity very well, but they don't always, depending on what state they're in. So what's next on the list? I have to grab some matches. What's that? Yeah, the liquid version of this. So one thing about potassium chlorate is its lattice isn't as strong. Like for example, if I tried to melt barium sulfate has a very high melting point. But potassium chlorate has a much lower melting point. Can you think of a reason why?
Why is it better than the salt?
Why is potassium chlorate so much easier to melt than other salts, maybe, is one thing. Like, for example, have you ever tried to melt table salt, sodium chloride? Does it melt? No. It doesn't melt. It has a very high melting point. Potassium chloride has a fairly high melting point, but potassium chlorate has a lower melting point. Barium sulfate has a very high melting point. Barium sulfate would be a lot harder to melt than sodium chloride. Why is that? Well, when you melt it, what do you do? What happens? Yeah, when you melt it, you're going to break apart the lattice. And so what I'm going to do is I'm just going to heat this up until I melt it. And this is why I put the potassium chlorate into the crucible.
Can we turn off the light so we can see what it
Okay. Let's see. I forgot my webcam again. Let's see if I can capture this on video. So normally people hold the Bunsen burner in their hand. Do you know why? Because if it gets too hot, they can remove the heat. You know, some reactions, when they get too hot, they can go violent. And so if this starts to crackle and pop, I'm going to remove the heat. The other reason people hold the burner in the hand is so they can move the heat. Rather than heat just one pinpoint spot, they can more evenly distribute the heat by moving it around. So burners are oftentimes held in the hand to heat things up. This gives us more control. All right, do you see what just happened?
No.
I just melted it. And when you melt it, then you break apart the lattice, and then you have a lot of, heat. Heat is going to be related to, or temperature is going to be related to what? Yeah, kinetic energy, motion.
So even in a liquid state, would potassium chloride be stronger?
What?
In a liquid state with
Well, it depends on what definition we're using. Now we're gonna stick with one definition of the strong electrolyte. The strong electrolyte definition we're sticking with is which one? The one we're sticking with is the one that when you dissolve it in water, it breaks up into ions. The reason we're doing that is because of our equations. The chemical reaction equations that we're writing, that would probably be the best. But there are multiple ways, so I wouldn't get too hung up on strong electrolyte, precisely defining it. And so in this case, what we have is we're interested in electrical conductivity. When we're interested in electrical conductivity, why is KClO3 liquid? A good conductor of electricity. And so what we want to do is we don't want to answer this based on electrolyte. We don't want to say, oh, it's a strong electrolyte now. Well, why is it a strong electrolyte now and before it was not a strong electrolyte? So you're using the electrochemist definition of it. What we're doing is we're just going to look in terms of conductivity. Now it's going to be a good conductor or a high conductor of electricity because of what? Mobility. Right. And so in the molten state, the ions have now translational motion. It's a liquid, and liquids can move in any direction they want, right? I could pour liquid, etc. The ions are still kind of attached to one another because the liquid doesn't fly apart into a gas. But now we have mobility.
So we're using the Coulomb's law, or the alpha definition. We're going back to the equation, the alpha, that we're using.
The sigma equation.
The sigma.
Yeah, this is conductivity, right? You can see that it's still conducting electricity because as the ions conduct, they're undergoing collisions and it's keeping it hot. And so what I'm going to do is I'm going to let it cool down. Because this is just going to keep conducting and it's going to generate enough heat that it keeps it molten. Oops. And so what I need to do is I need to cool it down a little bit and let it solidify. Once it resolidifies, you know, right, if I look down into the crucible, I have a liquid potassium chlorate salts. Liquid molten salts are very interesting. There's a documentary on YouTube about refining aluminum ore. And aluminum ore comes from bauxite. Bauxite's very common, but bauxite is extremely hard to melt. You know, barium sulfate, I told you, was extremely hard to melt, but look, do you know what bauxite is? Bauxite is Al2O3. What's the name for this, Al2O3?
Aluminum-3 oxide.
Aluminum-3, okay, what are the other charges for the aluminum ion?
There's 3, and then there's only have 1. Or is it 1?
Well, take a look on the periodic table here. What are the common charges for aluminum?
Plus 3.
Plus 3 and what else?
-6 or 5.
Well, -5 is going to be tough to do. It's too many electrons to hold on to. But that's the range. I'm not talking about what's the range. I'm talking about what is the most common charge, not the range.
Common charge is
3. Is there any other common charge for aluminum?
I wouldn't think so.
No. So we wouldn't call aluminum 3 unless there are multiple charges that are common.
would just be aluminum oxide.
Yeah, this is just called aluminum oxide.
And it has a high melting point.
Yes, why? Tell me in terms of Coulomb's law why it has a high melting point.
It's solid and it has low translational mobility.
All solids have 0 translational mobility except the superionic conductors I showed, and even those have restricted translational mobility. It's restricted only to certain ions.
So the ions can't really move around. They don't have kinetic energy. That would make it harder for it to melt.
Let's say if the one thing about kinetic energy is if I have some potassium chlorate, which is easy to melt, versus some aluminum oxide, which is hard to melt, and they're both at 25 degrees C, does the potassium chlorate have higher kinetic energy than the aluminum oxide? They're both at 25 degrees C. Do you guys remember this? This is from exam 1. I asked a very similar question on exam 1. Well, this is another tip. Another tip is when I was a student, I used to just focus on the next test. What was the material for the next test? But when the final came around, it was from the beginning. Most of the classes I had were comprehensive finals, not just from the last test to the final. And so another thing I did to improve my test scores was to start reviewing for the final at the beginning of the class. So what I do is I just go back and review. And so the earlier stuff I used to forget, but if you review it, you won't forget it as easily. So you just go back. So I mentioned that I reread my notes, and I try to have a comprehensive set of notes, but I reread them from page 1 all the way to the current page every day. That was probably one of the biggest things that helped me for studying for finals. But getting back to this, do you guys remember that question on exam 1 about the kinetic and potential energy?
Yeah.
So it was something like a stick of dynamite versus a stick of wood at 25 degrees C. Which one has higher kinetic energy? Neither. They both have the same kinetic energy. And so the kinetic energy, what it is we're measuring, they both have the same average kinetic energy. So when we look at it, the heavier ions are going to be moving slower, but the lighter ones are going to be moving faster. But the odd thing is they're going to have the same energy. Even though the light ones are moving faster and the heavy ones are moving slower. Because energy, if you take physics, kinetic energy is given by Newton's law, 1/2 the mass times the velocity squared. So if the mass goes down, the velocity goes up, but the energy stays the same. And temperature is just directly proportional to the kinetic energy here. And so we can't use kinetic energy arguments because aluminum oxide and potassium chlorate have the same kinetic energy average. Yes, one could be moving faster, but according to Newton's laws, it's the same energy. And so we have to come up with a different. It's like, you know how fast the nitrogen molecule's moving in this room? It's moving fast. Over what was it? Over 1,000 miles an hour. It's moving at 1,000. If a nitrogen molecule hits you at 1,000 miles an hour, do you feel? I guess we do feel it because it's 15 pounds. But you wouldn't feel it like if a car was moving at 1,000 miles an hour and hit you, you'd feel it, right? Because, yeah, you'd be dead. And so the energy depends on both on the mass and the velocity, not just the velocity alone. And so we do that in combination. But this is physics.
Are you saying it's because the aluminum oxide has like a high mass?
No, not at all. We don't care about the mass. I care about something else. Does Coulomb's law ask you for the mass?
No.
No, what does Coulomb's law ask you for?
Distance and charge.
Right, and so we have to argue in that sense because people are going to understand Coulomb's law. If you start throwing in, does Coulomb's law depend on kinetic energy? No, it doesn't. Coulomb's law depends on charge and distance. So when you start adding all these extra things, it's just mixing things up. I mean, there could be some side relations. Yes, if you have high energy, then the distances vary a lot more because you got bigger vibrations. And therefore, the average distance might be larger or shorter or something, or those types of things. It's easier to break when the distance, when the vibrations get so big and the distance gets to a certain point, then it's easy to break off. This is why temperature can have an impact. And so when we talk about science, we try to have it like this, where we look at what variables impact it. And so if I'm asking about melting point, what variables impact that? So I already talked about it. I was trying to infer this so you would pick it up, but what I was trying to infer is the stronger the lattice, the harder it is to dissolve and the harder it is to melt. And so what makes a strong lattice? Well, we talked about barium sulfate compared to some of the other lattices. Barium sulfate has a strong lattice because of its
Charge.
charge. Well, what about aluminum oxide? What's the charge on aluminum? +3. What do you think that's going to do to Coulomb's law? It's going to make the force greater. Oxide's a -2. So +3 -2 is a total of -6 compared to +2 and -2. +2 and -2 is -4. And so we're going to have a stronger lattice because the forces holding the ions together are going to be greater.
We're not worried about size yet, right?
We're not worried about size. We got to throw in size later. The only time I talked about size was in relation to the proton. Does anybody remember what I said last week and what I said yesterday about the proton?
The neutron, the proton, it's like this is
Proton's small. We don't care about the neutron. Neutron's separate, though. Neutron is very small also. But the one thing about the neutron is, does the neutron have any charge? No.
it's not really that important.
Neutrons are very dangerous. Neutrons are very dangerous because they don't have a charge. Yeah. And so neutrons, you have to watch out for exposure to neutrons. Like if a proton approaches a nucleus, it gets deflected. If a neutron approaches the nucleus, it doesn't get deflected. And it can get absorbed into the nucleus and cause it to screw up the compositional ratio, making it radioactive. And so neutrons are dangerous. Neutrons, I talked about the fusion a little bit. You have to accelerate these particles to extremely high speed to get them to collide and fuse together.
What do you do with hydrogen and helium, correct?
Right, heavy water. The heavy water and nuclear fusion. In the sun, you can get very high speeds because the temperature is extremely high. Million Kelvin or whatever it is. Okay, so let's go back to this. So the potassium chlorate solidified. Is it conducting anymore? No. So one way to get mobility is to melt it. Another way of getting mobility is that, yeah, it's potassium chlorate soluble. Chlorates, and what else? Chlorates. Well, actually, we'll go on with the pattern. Chlorates. Well, there's 3 anions that chlorate is paired or grouped with. Acetate, yes. Chlorates, acetates, and nitrates, yes. Yeah, don't call it ammonium. Ammonium is a cation, NH4+. Ammoniums are also soluble, but we group ammonium with what? Group 1. And so chlorates, acetates, and nitrates are all soluble. What are the exceptions? Yeah, there are no exceptions. So this is going to be water soluble. So another way that we could free it up is it's a soluble salt. Soluble salts are strong electrolytes. So all I'm going to do is I'm going to pour some water in here. And let's see what happens. Yeah. No. It doesn't have to be a metal. Like, for example, ammonium chloride has no metal in it, but it's considered a salt. Ammonium chloride salt. I gave another definition. Does anybody remember the definition I gave yesterday for a salt?
Ionic compound?
Ionic compound. A salt is an ionic compound that is not an acid. Acids could be molecular or ionic depending on how strong the acid is. There are some superacids that are quite ionic. But acids, since acids we treat differently, we call those acids, and salts are just any other ionic compound. And so rather than saying ionic compound, which is quite a lot to say, we'll just say salt. It's a lot easier to say than ionic compound.
So acids that are ionic compounds are not acids or salts.
Ionic compounds could be either acid or a salt. So therefore, if we say salt, what is a salt? Salts are all ionic compounds other than acids. So it's just, if you think of it mathematically, you could think of it like something like this. Ionic compounds equals salts plus some, not all acids, we'll just say some acids. Because some acids are quite molecular. And therefore, salts are equal to ionic compounds that minus acids, some acids. And so if we think of it mathematically, this is what I'm saying. Salts are ionic compounds except some acids. Ionic compounds, we can group everything in together. Because we have well, so far we have two types of compounds, but there are more.
It's a little vague, but I guess the categorization a little bit to get to know the acids and ionic compounds and stuff.
Yeah, all the acids we encountered begin with an H. And so this is why when Jacob was saying about they have metals, yeah, most of them do have metals, because they begin with a metal or ammonium or ammonium derivative. Ammonium derivative is we have a lot of things that are like ammonium, behave exactly like ammonium because structurally they're very similar. So we have something called methylamine, which is just like ammonium except we replace one of the hydrogens with a CH3. And so that's like ammonia, and then we can make this like ammonium by upping the hydrogen. So this is called methylammonium ion, which is just like ammonium in a lot of ways. This is a side. Amines, we'll talk about those in Chem 1A in more detail. We'll talk a little bit about them in Chem 4. So in KClO3 liquid, we have potassium ions in the liquid state. The liquid state just means they have mobility. And we have chloride ions in the liquid state, which means they have translational mobility.
Just to be sure, first to make sure I'm correct. If anything is put into a liquid state, it's still the same properties before, it's just now translation.
Yeah. If it's a ball, we don't consider rotational motion. Balls can do whatever. It doesn't take any energy. It has to be a more complex shape to have rotational motion. So spherical things are just usually just translational only. A ball. We don't think about this ball spinning. If it's a perfect ball, perfect sphere. KClO3 aqueous consists of potassium ions, aqueous, and chloride ions, aqueous. And so aqueous ions will have translational mobility. And so we should get good conduction of electricity. So,
There's no species, right?
no. Potentially, depends if it's saturated or not. We can't dissolve an infinite amount, and so there could be some solid remaining, but not in this case. There are no minor species. This is it. Later on in Chem 1B, you'll learn about other species that can form. The other species are simple. We have something called an ion pair, where the potassium and chlorate, they aren't strongly enough attracted to come together to precipitate, but they are attracted enough that when one potassium passes by chlorate, they slow down. And for that one moment where they slow down, they're pair, and then they go their way. And so that slowing down when they become a pair can impact their behavior. They aren't completely independent of one another. But they don't slow down where they bond together and precipitate. And so we could have ion, well, these are called ion pair formations. This is Chem 1b. No, this is Chem 1a. But not Chem 4, so we're not going to worry about it at all. Next one is table sugar. Solid table sugar. Do you expect it to conduct? Solid table sugar? I didn't dissolve it all here. There's still a chunk of solid potassium chlorate stuck on here. All right, for table sugar, let me ask you, solid table sugar, does it have mobility? No. Therefore, if it has zero mobility, what do we expect for the electrical conductivity?
No conductivity.
Yeah, well, very little would, you mean the sugar molecules have a little bit of mobility? Is that what you mean? By very little. What? Very little because why? You have to, in science, you'll have to argue your point. That is, one of the things in science is people like scientific debates because, nobody knows everything. And so it's always good and healthy to have scientific debate. And so somebody might say, well, I don't believe you. A little bit? What are you talking about a little bit? Explain to me. And then you would say, it would have a little bit because...
I just think it's iron as a solid before, and that was able to
so we did iron before, and it was able to conduct electricity. So table sugar is like iron. In what way is it like iron?
solid as well.
So all solids can conduct electricity, even glass. Or if I use a ceramic insulator, aluminum oxide is used as an insulator for a lot of applications. And insulators, if we have a high voltage line, you want something that doesn't conduct any electricity for a high voltage line. And so what would be good to use in that case? And so, in other words, where does the little bit of conductivity come from? You would say the little bit of conductivity comes from what? Okay, you could say I'm just guessing, or that's speculative. That's fine. I mean, people can do that. There's nobody going to argue about that. But
Would we use like iron as a superconductor or something like that? That's why it would bulk.
I'm sorry?
Because iron was like a superconductor, so one of the exceptions.
Ion is a superconductor? Iron? Iron's not a superconductor unless you cool it down. Room temperature iron doesn't superconduct. But if you cool it down, what happens? Why do certain metals start to superconduct at low temperature? Somebody
Because it's translational motion, or I guess close to translational motion.
no, not that. That's not the reason. Translational motion is very critical for it, but there's translational motion at room temperature for the electrons. So what's the difference? You got translational motion. This doesn't superconduct at room temperature. This is iron. That's not superconducting, but that's the electrons. We have translational motion of the electrons. This is iron here. So when you go to talks and conferences, at the end they like question and answer, and it's like an oral examination. Sometimes you think, wow, why are they so on this speaker? And it depends on what the speaker is saying. And it's not that they're trying to be mean, although sometimes you think, wow, they're really being mean to this person. I was watching, I've been watching some physics videos, string theory and stuff. Now, there are people who are just totally think string theory is some ridiculous speculative fabrication, multiverses and all this stuff. And so it was kind of, and then the counter arguments to string theory. I mean, there are some, strong believers in string theory, and the strong disbelievers in string theory. And it's really interesting debate about string theory. String theory is kind of, a lot of these movies where they transition through some wormhole into some other universe, it's all part of string theory. And some people think that's ridiculous fantasy land stuff. Other people think this is good solid science. And so there's a pretty good debate about that. But anyway, what you want to do is, if you want to think about, certain things like, okay, why do you think it would be a zero conductor? So tell me why you thought it would be a zero conductor. Yeah.
Based on the patterns, maybe it's solid, except for iron.
Okay, it's not because of solid. You have to start thinking about what makes something conduct electricity versus something that doesn't. Because all right, that's fine. It has no mobility, so it won't turn on. And so we see no light there. But what would the argument for a little bit of light be? That it has a little bit of mobility?
Because it's high charge and high number.
Okay, well, sucrose, let's take a look at the sucrose molecule. What ions does sucrose consist of? C12H22O11.
Carbon, hydrogen, oxygen.
Okay, those are the atoms it consists of, but what ions does it consist of? The elemental makeup of sugar is carbon, hydrogen, and oxygen.
Carbon 4.
Carbon 4
Hydrogen plus 1 and oxygen minus.
minus 2. And then it all separates. You got your mobile carbon 4, your hydrides, and your oxides. It turns out that carbon isn't even plus 4 in this. Carbon's less than plus 4. If carbon was plus 4 here, it wouldn't burn. In fact, carbon is 0 in this. And that means that the carbon has the capability of going to plus 4. And so if carbon's in the 0 state here, then it's possible to burn sugar. Does sugar burn? Yes, sugar burns. That's why I would try to melt this, but it's hard to melt sugar because you know what tends to happen rather than melting the sugar? It starts to caramelize and then it'll start to burn. And so I'm not going to melt this. But even if I could melt this, if there's no oxygen around, then no problem. I could melt it. But since there's oxygen around and it gets hot, then it'll start to burn because carbon is in the 0 state in sugar, and it could go all the way to plus 4 to make CO2. If you eat sugar, do you know your body burns it metabolically, and you exhale CO2, but CO2 is the final end product. There's no more nutritional value you can get from CO2. and therefore your body makes full use of the sugar. That is, it completely oxidizes it. If you're exhaling carbon monoxide, there's still more energy content there because you can still burn carbon monoxide. But you don't. You exhale CO2, you completely metabolize it. In other words, you completely oxidize it. And by doing that, you're extracting the maximum amount of energy you're going to get from the sugar. Uh-huh.
Does sugar, would you say it dissociates completely in water pretty well? Or
Okay, it depends on what you're talking about. If we have compounds of nonmetals are molecular or ionic? Molecular. So nonmetal compounds are molecular, except for ammonium and ammonium derivative, like ammonium chloride. Ammonium chloride, even though it's all nonmetals, we think of that as ionic because it contains the ammonium ion and the chloride ion. But something like this, we don't think of containing any ions. And this would be purely molecular. And so what happens is, if we were to look at the lattice of sugar, actually, maybe since sugar is a bit harder to draw, let me show you what I'm talking about here. These stick diagrams represent a sugar molecule. So this is one sugar molecule here. This is another sugar molecule, another sugar molecule. So the sugar molecules in a sugar crystal are packed together, and it's an orderly arrangement, so it makes nice crystals, even though it doesn't look so orderly here. But there's no bond between the sugar molecules. These are standalone entities. And so when we say dissociate, there's two ways of thinking about dissociate. The way we've been thinking about dissociating is dissociate into ions. Sugar does not dissociate into ions. But if we were to dissolve this molecule in water, what happens are the sugar molecules break apart from one another. What's holding the sugar molecules together? What's holding these sugar molecules together is something we call intermolecular forces, or hydrogen bonds. Hydrogen bonds are what holds like DNA in the helical arrangement. If you were to turn off the hydrogen bonds in DNA, the DNA would collapse into a spaghetti noodle. And so the DNA is held in this alpha helical structure by hydrogen bonds, and that's what holds the sugars together, sugar molecules together. And so what we can say is that what I can do is, this is just table sugar, and so what I'm going to do is I'm going to dissolve it. Does table sugar dissolve in water? Yes. And so this is solid. Solid does not conduct electricity, and you wouldn't expect it to conduct any electricity because, number one, no mobility. Number two, do sugar molecules carry a charge, a positive charge or a negative charge? No, they're neutral. And so we expect zero conductivity. And so this is why when you're saying a little bit of conductivity, then if you were at a debate, then somebody would debate you about that for sure. They'd pick up on that right away. Here, okay, now sugar is not infinitely soluble, but more than 0.1 moles dissolves in a liter. In fact, a lot more than 0.1 moles dissolves in a liter. And so you can make very concentrated sugar water, and it'll taste very, very sweet. But what happens when the water comes in, it's going to dissolve the molecules, and now the molecules will have translational mobility, but it still doesn't conduct. It still doesn't conduct because the sugar molecules are lacking charge. There's plenty of number here because we can make this very sweet, but it's not going to carry any electricity at all. In fact, let me see if I have sucrose is kind of important, but let's see if I have a molecular dynamics. Correct. Yeah, there would be no minor species. Yeah, they're all sugar molecules. The sugar molecules don't do anything. They don't dissociate. They don't do any of that sort of stuff. They're not a weak electrolyte. Weak electrolytes are weak acids, weak bases, and some heavy metal salts. Is sugar any of those? No. Sugar's not a strong electrolyte either. It's a non-electrolyte. Sugar is a non-electrolyte.
In this video, we'll look at the equation for sucrose. That's C12H22O11 plus H2O, water. You also know this
I was
as
expecting molecular dynamics.
grams
This
of
is
this
not molecular dynamics.
here,
Sorry.
because H2O put above
Should
the
look
arrow.
this up earlier. Okay, here, sugar and salt simulation. This is pretty cool.
Hey, what is up, everybody? Today, we are going to distinguish between different types of solutions. Sounds easy enough, right? It may not seem hydrogen bonds that we got my little attractions of sodium to chloride and chloride to sodium. Solute attractions. And then notice
is
my
not
water
molecular dynamics.
molecules
This is just a
in
cartoon,
my
so-
beaker
Here they put salt
are attracted to
and
one
sugar.
another. I'm going to show some of those
Sugar,
partial
bunch of
charges there.
molecules packed together.
And then I'm going to drop my solute in my solvent to
Here,
make a
this
solution.
differentiates into
And
ions.
notice the solvent
When it
molecules, water, will be
When sugar
attracted to the
dissolves, it
solute
associates with
particles,
molecules.
sodium chloride. So let's just
No,
put
that's
this in here and see what
solubility
happens.
question
Whoa,
here.
pause
We
it
know
there.
about
The
ions.
water
We know the
molecules have sort
hydrated
of
ions here.
the association
hydrated
of a soluble
ions.
ionic compound. Now, what results then is a solution,
Let's
negative
take a
chloride
look,
ions.
and this is just
Boom.
a dissolution
The
process.
hydrogen attracted to the chloride.
Let's see
Keep
if
in
we have
mind that
the
this
sugar.
also applies, but
Other
again, the
salts.
rate, I've got a
Same thing. Okay,
couple
here's
of
the sugar.
molecules of sugar that are right now, attracted to one another.
Molecules.
I'm going to
They
highlight them in
dissolve
yellow
also
so
in
it's
water.
easier to ones that make up the sugar molecule
They
are
just
not going
show
to
two
break
individual
apart.
sugar water
So when you shake a bunch of sugar
So they
into a
pour
solution,
sugar crystals in.
it's not like you're getting a bunch
sugar
of
crystals
carbon
break
ions,
apart
hydrogen
into
ions,
sugar
and oxygen
molecules.
ions.
The sugar
That's
molecules
an ionic
don't conduct
compound.
with
In a
it.
covalent compound, you're just going to get your
This is a
discrete
simple
molecules
simulation of it.
dissolved in solution. All right, now the last thing we need to talk about here is some quick vocabulary terms.
Anyway, back to that. I was talking about the refining of aluminum. I'll talk about that in the future, some other time. All right, let's stop here. We'll take a break. Actually, then we'll look at a few of these other ones. Slab. What's next is ethanol. And so the first thing we're going to look at is just ethanol liquid. This is pure ethanol. Pure ethanol, would you expect it to conduct? It's a liquid, so there's translational motion or mobility. There are lots of ethanol molecules, but what's missing in ethanol? The charge. Ethanol is molecular. It doesn't break up into ions. So when I check ethanol, do you see any electricity? No, that's pure ethanol. No, it's because it forms molecules. It doesn't form ions that the water molecules can tear apart. Yeah, it's not. The carbons, they can have what we call a parent charge. When we're calculating the charge of it, we use that for bookkeeping, but it's not necessarily what the ion is. So, for example, CO2 doesn't consist of a carbon plus 4 cation and oxide anions. It forms a molecule, and the molecule is really hard to break apart. Whereas ionic compounds, the waters can come in and tear it apart. And so the next one is ethanol aqueous. Will the water molecules break apart the ethanol molecules? And the answer is no. Ethanol aqueous just consists of ethanol molecules dissolved in water.
So there would be no minor species, just
No. No minor species. It's like sugar. Except pure ethanol is a liquid, pure sugar is a solid. Hydrochloric acid's next. Hydrochloric acid is a strong acid, weak acid, or
strong acid.
strong acid? And so what do you expect? Strong acids are strong electrolytes? Strong electrolytes? Yeah. So hydrochloric acid, excellent conductor. What's next after hydrochloric acid? Sulfuric acid. Strong acid? Yeah. Strong acid is a strong electrolyte. What does sulfuric acid dissociate into? You'd expect it to dissociate into sulfate, but it happens one step at a time. So sulfuric acid is a strong electrolyte. One hydrogen breaks off at a time. And so what happens is, it's kind of weird. And so we do this in equations as well. And so I skipped the ethanol and HCl, but for sulfuric acid, it's a strong electrolyte. But what happens is just the first hydrogen breaks off easily. The second hydrogen doesn't. So this is strong. But HSO4 is not strong. HSO4 minus is weak, which means that the downhill direction is reversed here. It likes to stay as HSO4. And so the major species are H plus and HSO4 minus. These are the major species. The minor species will be sulfate. We don't form as much sulfate here because HSO4 minus itself is a weak acid. Weak acids only partially dissociate into ions. And so when we're thinking about H2SO4 as far as the major species in solution, just these come into mind right here. Okay, what's after H2SO4? Acetic acid. Acetic acid is strong acid? It's a weak acid. Are we looking at pure acetic acid, liquid, or aqueous? We're looking at aqueous acetic acid. And what do you expect for the light bulb? Dim or bright? Dim. So it's dimmer, but it's still fairly bright. It's dimmer than HCl. Yes. Right. Yes. No. That's not the major species. Yeah, that's the minor species because it's a dim light. And so when we're looking at acetic acid, It's a weak acid. Weak acids partially dissociate into ions. The ions would be H plus and acetate, mentioned. This is the major species. This would be the minor species here. This is uphill. This is uphill, downhill is much more favored. Okay, after acetic acid, aqueous, we have what? Yeah. Acetic acid liquid. This is pure acetic acid. Let's take a look at that. Do you see much of anything? Let me turn off the lights. You might smell it. It smells like vinegar. Do you see anything? No. Why is that? Right. We need water molecules to tear apart the molecule. Like we need water molecules to tear apart the ionic lattice. Glacial acetic acid, this is just pure acetic acid, so it's just the molecules stay together. Uh-huh. Liquid is a mixture. Aqueous is, actually, liquid is not a mixture. Liquid is pure. Liquid is not molten. Well, it is molten at room temperature. This is normally a liquid. And so we don't normally call it molten. We just call it a liquid. Molten, we usually refer to something that's a solid at room temperature, and then we elevate the temperature to melt it. And that's usually it. But acetic acid normally is a liquid. And so in water, the some of the water molecules can form hydration spheres to isolate and stabilize these ions. And so we have aqueous ions here. But in the pure state, there's nothing to help tear apart the molecules. And so when we look at just HC2H3O2 liquid, we need something to hit the molecule and break it apart. There are other molecules in here, but we need water molecules to come in here to break it apart. And so an abbreviation for acetic acid is HAC, AC for acetate. And so all these are HAC molecules in the liquid state. So they have translational motion, but they aren't broken apart. There is potential that they could break apart from collisions, but by having water there, water tugs on the ions here and hydrates them. And so water is important in dissociating these and stabilizing these. And so, and that. After liquid acetic acid, we have, what's that called? NaOH. Sodium hydroxide. Sodium hydroxide is a sodium salt. Sodium salts are all soluble. Strong electrolyte. Yeah. So we get a bright light. And so the water will break apart the sodium and hydroxide to form sodium ions AQ and hydroxide ions AQ.
Would there be minor species though, right?
No, it's soluble. Soluble salts, we just say there are no minor species. Okay, next we have barium hydroxide. Barium hydroxide. Hydroxides are all soluble or insoluble. All insoluble.
Still with barium.
Yeah, barium is an exception. And so it's a soluble salt. Soluble salts are
Ionic sulfur acids, or they are strong electrolytes.
soluble salts are strong electrolyte. But
It's a great property.
with barium hydroxide, when we say soluble, right? When we say soluble, it just means it's more than what? 0.1. What if we're close to 0.1? Is that very soluble? No, that's borderline. And so if you look at how bright this is,
It's slightly soluble.
it's not bright. Maybe it's more slightly soluble. We still call it soluble, but its solubility isn't so high. But what does dissolve will break apart. So we still call it a strong electrolyte, but it just doesn't have the solubility of sodium hydroxide. Sodium hydroxide had a lot more.
Now we have ammonia.
Ammonia. Ammonia is molecular, so it shouldn't conduct electricity, right? But what did we learn about aqueous ammonia?
It's an exception.
Exception in what way? Well, what we learned about aqueous ammonia is not necessarily it's an exception. We learned that aqueous ammonia is a weak base, and weak bases do what in water? They weakly hydrolyze water. So if we look at aqueous ammonia, it shouldn't conduct. Because ammonia, does ammonia molecules have any charge? No. But ammonia can react with water to form what? A little bit of
Ammonia and H2O, which is
NH3 plus H2O makes,
ammonium hydroxide.
yeah, and ammonium hydroxide will conduct. And so we expect some ammonium and hydroxide to exist in here, and so we expect some current. And that ammonium hydroxide can participate in metathesis reactions that we were working on yesterday.
So our main species will be ammonia, but our minor would be ammonium hydroxide.
Yes, exactly. All right, we're going to stop there. For this report, you don't have to do this. Okay, for this report, you don't have to do actually, we'll just do it. These aren't that bad. Number 5. So omit number 5.
Just number 5.
Yeah, just number 5. Yeah, omit number 5 on page 5-4. Did everybody get that?
We're gonna do it.
Huh? Don't do it, yeah. 1 through 4. Right.
Don't do 5.
Don't do 5. It'll save you a lot of time. All right, let's go on to experiment 6. Here's some abbreviations that you can use for experiment 6. PBT I've talked about. Clear, that's not an abbreviation. Effervescence, EFF. Solution, SOLN. Clear colorless solution, CCS. Clear colorless gas, CCG. clear colorless liquid, CCl. Some abbreviations for colors. You want to use those. Then we're going to be looking at some reactions. So some of these reactions we'll see. On the test, I'm not going to give you the formula. On the test, you'll be given the name, and then you'll have to figure out what happens here. And so we'll look at a series of reactions here. And so what we'll do is, let's see, what time is it? 11:46. What we're going to do is we're going to first predict, or do you want to first observe? Maybe let's first predict what's going to happen. And so why don't you start working on these here and predict what's going to happen in your notebook, and then let's take our observations of what actually happens. So again, on the test, you're going to have to figure out the formula. So if I tell you hydrochloric acid, what's the formula you'll write? Yeah. Okay, if I say sodium carbonate, what's the formula you're going to write? NaCO3 is incorrect. It would be Na2CO3. Na2CO3 would be correct. A lot of these are quite similar. Potassium carbonate, sulfuric acid, sodium carbonate. So what we want to do is we want to write the CE, the IE, and the NIE, and then predict the driving force. So why don't you do number 1, number 3, one, 3, 5, seven, 9. We'll just do the odds for right now. So just work on the odds. 1, 3, 5, 7, 9. What you want to do is you want to make sure that you can write the formula for all these. These are very common chemicals here. So you should be able to write the formula and then do the double replacement reaction, the AB plus CD pattern, and then figure out what we're going to form. So. When we do these reactions, you have to do the formulas as you would in normal nomenclature. So, for example, sodium carbonate. How do we figure out the formula? Well, it's given there, but you have to figure it out yourself. How do we know what the right ratio between sodium and carbonate is? Well, number 1, oops. Next week's test is going to have a lot of nomenclature on it. And if you don't get the ratios right, there's not much partial credit given here. So how do I figure out what the ratio is? First, you got to get the right ions. So either you have these memorized by flashcard, or you memorized it some other way, or you're able to derive it. But the first critical point is, what is sodium, what is carbonate? Once you have sodium carbonate, is this the correct ratio between sodium and carbonate? No. Why? Why do you need two sodiums? Why can't I just do this? Yeah, it doesn't balance out the charge. Sodium is only a +1, and it won't balance out a -2. So if I put these 1 to 1 like this, then I'm still going to have a negative charge that's not balanced. The same thing with H. H is, what's the charge on H? Plus. And what's the charge on carbonate? And so what's the right ratio between H and CO3? I see a lot of people writing this. This is wrong. Why? There's two hydrogens. That's why this is wrong, because there's two hydrogens. Why do we need two hydrogens? Yeah, so it cancels out the negative charge. So two positive charges will cancel out this -2. Two positive charges will cancel out this -2. So this is wrong. The correct formula is Na2CO3. It doesn't matter how many they give you, because we don't balance it now. When we try to get the formulas correct, we ignore balancing. So if they only have one H on the left side of the reaction, like HCl only has one H. Wait a minute, if HCl only has one H, then how do we get two H's? Well, the way we get two H's is we balance it later by multiplying HCl by 2. Now we have two H's. So don't worry about if it doesn't balance. We're not trying to balance and write the correct formulas. All we're doing is we're writing the correct formulas first, and then we're balancing it later. So completely ignore the balancing part now. Now, once we have H2CO3, I told you H2CO3 is one you have to memorize because it's unstable. What does it decompose into? Yeah, okay, so some people have it memorized already. If you don't have it memorized, you need to have this memorized by next week. It's going to decompose into water and carbon dioxide. I don't care if you leave out aqueous, but if you leave out aqueous, you better have liquid, gas, and solid. If you don't have liquid, gas, and solid, you're going to lose a lot of points. So make sure if you don't write aqueous, that's fine. But if you don't write liquid, gas, and solid, that's not fine, and you're going to lose points. I'm going to deduct a lot. And so the thing is, if on nomenclature next week you write HCO3, unfortunately you've just lost a lot of points. So make sure you don't make these mistakes, and then you can maximize the number of points. I mean, this is not terribly difficult. I'm sure once you see this, you go, oh yeah, that makes sense, because we need two hydrogens to balance out the charge. What's that? H2CO3 is one of the products, but what we do is, what was the other product? H2CO3 is one of the products, and the other product is NaCl. NaCl, I saw this because, what was it? I saw this, and the reason why people write this most of the time is because we're using sodium carbonate. And sodium carbonate has two sodiums, but sodium chloride does not have two sodiums. Just because sodium carbonate has two sodiums, don't make sodium chloride with two sodiums. How many sodiums does sodium chloride have? One. And how many chlorides? One. And so I don't let sodium carbonate impact how I write the formula for sodium chloride. Sodium chloride is always the same. It's H2O. And the same thing goes with water. You know, I don't like say I had 4 hydrogens over here. I don't write H4O because I had 4 hydrogens over here. Water is always water, and water is always H 2O. Sodium chloride is always sodium chloride, and sodium chloride is always NaCl. Carbonic acid is always carbonic acid. It's always H2CO3, and I wrote a little asterisk here because it decomposes. It decomposes into water and CO2. And so what we do is we write a line through the sodium carbonate showing that it decomposes and forms H2O and CO2. Okay, so what we want to do is we want to write the CE, the IE, and the NIE. So number one, they give you as an example. So sodium carbonate and HCl. It doesn't matter what order we write these in, but it does matter what order we write these in. If somebody saw this, is that table salt to you? Is that table salt to you? No. There's an order to this. We always write the cation first. We always write the cation first. So don't reverse it. Don't go carbonate and then sodium 2. People will wonder, what the heck is that? This does not look like sodium carbonate, whereas this does. So the cation always goes first. However, the order, I could put HCl first or sodium carbonate. It doesn't matter here. And what does this form? And sodium chloride. So that's what we got so far. The H2CO3, we have to remember, decomposes spontaneously, immediately to okay, and then what we need here is we need to balance it. To balance it, I have 2 sodiums here. I'm going to need 2 sodium chlorides. That gives me 2 chlorines here. That means I need 2 HCl's here. 2 HCl's will give me, I have 1 carbonate and then 1 carbonate here. I balance it using carbonic acid. I don't balance it using H2O and CO2 because it's more of a headache. And then I have 2 H's, I have 2 H's here. And so it's balanced. Yeah. Okay, now this is the CE. What's the IE? Yeah, HCl is a strong acid, so it goes to 2 hydrogen ions and 2 chlorides. That's correct. What about sodium carbonate? 2 sodiums and 1 carbonate. No, we don't write H2CO3 in the ionic. We're just going to write this. H2O liquid and CO2 gas and 2 sodiums plus 2 chlorides. Okay, and then the NIE? What are the spectators here? Carbonate's not a spectator. I have carbonate here, but I don't have carbonate over here. I have CO2. CO2 and carbonate are 2 totally different things. Yeah, sodium and chloride are spectators. So the NIE is just going to be carbonate, 2 H pluses, yields. Yeah. What's the driving force for this? Precipitate usually refers to a solid. We're not forming any solids here. Yeah. Driving force would be gas formation. There's one more driving force. Do you see it? Yeah. So stronger acid to weaker acid. The stronger acid is HCl, the weaker acid is carbonic acid, which decompose. Do you know CO2 is considered an acid too? This is also weak acid.
We wrote our answer as, for example, H2CO3 and then do the line through and then the net. And we do that and then we do the H2O plus CO2 that we got.
Yeah. That's okay too. All right, work on number 3, and after you're done with number 1 and number 3, we're going to, and 1, 3, and 5. After you're done with 1, 3, and 5, let me see what 3 is. 3 is sulfuric acid and sodium carbonate. 1, 3, 5, and actually, let's just do that. We're going to do number 1 and 3. After you're done with number 1 and 3 here, you can grab a pair of goggles and 2 test tubes, and then we're going to go over there. And then what we do is we're going to put a squirt of sodium carbonate into the test tube and then drip the acid in. There's a safety rule called AA. AA stands for always add acids. Always add acid to whatever. Don't add whatever to acids. The reason is because of heat. You know, it can get very hot if you add, let's say, for example, water to acid. And so add acids is the safety rule. And so put a squirt of sodium carbonate and then drip the acid in. And so we're going to have 2 test tubes, one with sodium carbonate, another with sodium carbonate. Test tube 1, we're going to drip HCl in. Test tube 2, we're going to drip sulfuric acid in, and then observe what happens. But before you do that, you take a look at the observations of this. So did you catch, how would you say hydrochloric acid is? Well, I'd say as far as observations go, hydrochloric acid is what we call CCS. And so here, hydrochloric acid is a CCS. CCS stands for clear colorless solution. It just looks like water, but don't drink it. Jason, don't drink the HCl, please. Sodium carbonate is also a CCS. Sodium carbonate's a white solid. It dissolves in water, but when we form this salt water, it's a CCS. CO2 is a CCG. H2O liquid is a CCl. And sodium chloride salt water is a CCS. You can't tell the difference. It looks just like water. So those would be the observations. Now the CCG is effervescence. Effervescence is EFF of a CCG. Those would be typical observations. And so what you'll do is you'll do that. You can wear gloves if you want. If you have a coat, you'll need goggles. If you don't have a pair, you can use a used pair over there. You can just clean them off. But the solutions are over there in the beaker on the middle bench between the 2 hoods. And so what you'll do is first do it on paper and then do it in practice. People are going to finish the equations at different times, then that will prevent crowds from forming up there, I think. So we should be all right. Anyway, I'd like to see your equations before you go up and do that.